Right now we're going to talk about what we call restrictions that exist for the inverse cosine function, inverse sine function, and inverse tangent function. And basically talk about how do I know which answer we want to give. So here's kind of what I mean by restrictions. If you were just dealing with the regular, let's just work with the regular sine function right now. So this would be y equals sine x. Okay, or sine theta, however you want to view it, where this is x, this is y. The standard sine function, it looks like this, right? But then, this is one period or cycle, but it continues, right? And it just oscillates like this forever in both directions. And with the standard sine function here, the inputs, which are your x values, are angle measures. So we often refer to it as theta here, and the output would be the vertical distance that the point is on the circle. So this would be a +1, this would be a -1 here, because the circle hits a maximum point of 1 and a minimum point of -1. But when we talk about the inverse function, you have to remember that everything is switched. So the input on the standard function, x, is the output when we deal with the inverse function, y, right there. And then also the output of the standard sine function, y, is now the input of its inverse sine function there. Another way to kind of look at this is if I just pick the 0.1/2 right now, and I just look at, all these values on the graph here have, an output of about 1/2 right now. So that would be this point, this point, this point, this point, the point that you can't see right here, the point that you can't see right there, and so on. So there's an infinite set of outputs on the blue curve that all have a value of 1/2 here, right? Which means there's an infinite number of angles as input values that produce an output of 1/2. When we work with the inverse function here, you're right, we want our inverse to actually reflect a function, basically. And since all of our inputs, since for the standard sine function right here, we have an infinite number of inputs that all produce an output of 1/2, when we work with the inverse function here, that means there's an infinite number of output angle measures that the inverse sine function can produce, all for the input value of 1/2 here, right? Everything is switched, remember. So when we work with inverse functions, we want the inverse to actually become a function. So we restrict the domain of the inverse function, this function right here, so that its output does not repeat any possible values, similar to all of these different points on the circle. We don't want our inverse function to go and just list an infinite set of points. So we restrict it to a domain. And the domain we restrict the input to is all input values must exist between -1 and 1 right here, which means its output values, which are the angle measures, must also be restricted. So down here, the standard restriction for a domain function is all angles between -90 degrees and +90 degrees. Or if we're dealing with radians, it's -π/2 radians to π/2 radians, which sounds kind of funny because, this negative value right here. And I agree, that's kind of different. Here visually on the board, what I did was I shaded the two quadrants that correlate with the range and the domain of the inverse sine function. And it basically runs from -90 degrees or -π/2 radians all the way up to +90 degrees or +π/2 radians. It's this rotation right there. And we start with -π/2 because that kind of, it's one of the closer values to the origin here for the restriction. So it'll hit all sections of this curve. I guess I should say right here, -π/2. So it hits all sections of this curve from here to about here, which are basically all the output values that we want right there. And it's this window right here. And so each function, the inverse sine function, inverse cosine function, inverse tangent function, they all have unique restrictions that are different than the standard sine, cosine, and tangent function. So sine is your quadrants 4 and 1, and I like to look at it, the restriction should be one positive quadrant for sine, one negative quadrant for sine, and those two quadrants should be surrounding the y equals 0 value, which is why it's quadrant 4 here and quadrant 1 as opposed to quadrant 1 and 2. It's this whole region right here. And when we jump into inverse cosine, actually, excuse me, let's look at some examples right now. So first question is evaluating radians without a calculator. Sine theta is equal to -1 right now. So we're basically looking at what angles does the sine of that angle produce a -1. So remember, the input of this function is really the output of the standard sine graph, right? So I'm looking at where does sine equal -1 on my circle? So I have a point right here. This is the coordinate point 0, -1. My y value is -1 right now. And most people want to say that that is a 270-degree rotation or a 3π/2 angle, which it is. However, the inverse sine function right here is defined in between a certain interval of angle measures. And those angle measures exist from -π/2 radians all the way to +π/2 radians here. And there's only one angle in that interval that has a y coordinate of -1, and that's -π/2. So the inverse sine of -1 is -π/2 radians here. Sine equals 0, same thing. So we're looking at what angle measure does the sine of that angle equal 0. So I'm going to go around my circle. And I know that at this point right here, at this coordinate point 1, 0, my y is 0. So that would be this angle right here. So then I can turn around and say that angle in that shaded green interval, which is the defined interval for the inverse sine function, is 0 radians. Inverse sine of √2/2. So √2/2 should indicate a 45-degree angle or a π/4 multiple there. Again, so now I'm looking at, in this interval from -π/2 radians to π/2 radians, where's my output of my y coordinate equal to √2/2? So it's definitely not down here in this quadrant. And it's going to be right here. This is the coordinate point √2/2, √2/2. The y coordinate of this point right there is √2/2. So that's the angle we're working with. That should indicate if you're dealing with a 45-degree angle or a π/4 radian measurement, and that's it. So π/4 radians right